First talk of the afternoon is by Jon Chaika from University of Utah. It's going to tell us about Horocycle flow on moduli spaces of translation purposes.
So first of all, thanks to the organizers for inviting me to give a talk here. It's a really humbling experience. I didn't know Mariam as well as many of the people who will be speaking here, but I came out to Stanford once to give a talk, and I was surprised at how much time she set aside to talk math and how generous she was with her times and her insights, and how fun she was to talk math with. Okay, so what I'm going to be talking about today is about some features of the Horocycle flow on the moduli space of translation surfaces that is different than the phenomenon it can have in the case of homogeneous spaces. And there's this big, very successful program about using techniques from homogeneous dynamics and importing them to the space of translation surfaces, or moduli space of Riemann surfaces, which are not homogeneous spaces, but for very profitably using these ideas. And this is a point where this fails. That's kind of where we're headed. Okay, so what's the setting? So I want to, the first thing I'm going to do is I'm going to state some theorems of Ratner, and I'm going to state them in a very special circumstance. So both for closeness to the results I'm talking about, and also to make one of the theorems I'm going to state of Ratner's for ease of statement. So what I'm going to do is I'm going to imagine I have some kind of a Lie group, say SLNR, and I'm going to mod out by a lattice. So the quotient I have SLNR, say mod SLNZ, is going to have finite volume. So there's various ways you can embed this little thing here into the SLNR so that you can get an action of this one parameter group on SLNR mod SLNZ. In the context of Ratner's theorem, for the purposes of today's talk, will be rigidity results for ergodic measures for this action. Okay? And so the first thing to mention is she classified the ergodic measures of these things, and every ergodic measure arises for algebraic reasons. So in particular, there's an intermediate subgroup, which can, if I've got some kind of a ergodic probability measure on this space, then it comes from an intermediate subgroup, which HS sits inside and which sits in the whole group. And it's a nice subgroup. It's a closed subgroup. And there's going to be some point, and the measure is going to be supported on the orbit of that point, projected down to my space, which is just all of, say, SLNR mod SLNZ. So all of G mod gamma. Does that make sense to everybody? But the takeaway is that ergodic measures come for algebraic reasons, and they're all nice. Okay? So you can also ask topological questions. You can ask, well, what about the orbit closures? So I take a point and I look at its orbit under this HS, this 1S01 subgroup, and then I take its closure. Is this a nice object? And the answer is yes. And in fact, it's very similar to what came in the statement before. It's also going to come from an intermediate subgroup projected downwards. It's going to be an L orbit. Okay? So orbit closure, so not just invariant measures, but also orbit closures exist for algebraic reasons. And moreover, these two things travel together. So for each point, I can travel around the space according to my orbit, and I can ask, in terms of measure theory, what do I see? And what you'll see is you'll equidistribute according to a measure. In what measure? The measure that lives on your orbit closure from projecting down the Haar measure on this intermediate subgroup. Okay? So there's this. So not only do measures are nice and come from nice reasons, and orbit closures are nice and come from nice reasons, but they're paired together. This is how they. Okay. So these are Ratner's theorems. They're a great achievement in dynamics and extremely useful. And so the next thing I want to talk about is some results of Eskin-Mirzakhani and Eskin-Mirzakhani-Mohammadi, which proved analogs of this in the space of translation surfaces. Okay? So first off, I need to tell you a little bit about the space of translation surfaces. And in the last talk we saw, Ben's talk, we learned a little bit about what translation surfaces were. And I want to think of them as being points in a space of such objects. Not just in objects like this on its own, but it's in a space of these objects. So I've drawn a picture of these. And so what is a translation surface? A translation surface is a special, for the purposes of my talk today, it's a special metric on a Riemann surface. And it's a metric which has that the transition functions between charts on this surface are translations away from a finite number of bad points where they're cone angles of integer multiples of 2 pi. So that's what a translation surface is from my standpoint. And so I've drawn you a picture of the chart. This is what I've tried to do for this picture. So this purple side here is identified with this purple side here. This green side here is identified with this green side. The blue is identified with the blue, the yellow with the yellow, and so forth. Okay? And so what do I mean by the transition functions between charts? Well, if I leave one side, let's say at this part of green, I'll come in on the other side. The green sides are the same sides, right? And they're just identified. And so the identification is by translation because these sides come in parallel sides of equal length. Okay? So this green line is the same as this green line. So when I leave over here, I come in over here. And if you want to know the funny points that I mentioned, the vertices of these sides are these funny points that have different cone angles. And there'll be 2 of them in this picture, and they'll have each have cone angle of 4 pi. So are people with me at this point about what a translation surface is? Great. Okay. So now these sides are very important, and they describe a lot of the structure. So I can change these sides a little bit. Maybe I could wiggle purple down a little bit and at the same time wiggle the other purple down a little bit. Maybe I could extend the length of green a little bit, both of the greens, and I could get a different picture of a translation surface. And translation surfaces come in families based on varying these parameters, which are, in this case, 6 vectors in R2. But if you notice, my picture is kind of funny. I have 2 separate pictures that are glued along the blue and the red. I could stick one on top of the other, and I'd get 5 important vectors in R2, and I'd get 5. So I would have local coordinates given by R2 to the 5th, and these are called period coordinates. Oh, sorry. And moreover, I get a natural volume out of just varying these coordinates, which is just given by varying these, locally given by varying these 5 vectors in R2. And often it's convenient to restrict to the area 1 locus, which is just a hypersurface in this space. And by area 1, I mean this picture should have area 1, right? I could scale it downwards, it would have less area. So this is kind of a natural volume form on these spaces. Okay, so the context of Ratner's theorem was about this special 1s01, this special element of SL2R acting on a space that was a Lie group mod a lattice. And translation, the space of translation surfaces has such an action as well. So what I could do is I could start off with a translation surface like the one I drew for you on the left. This is secretly a torus, but let's ignore that fact. That's not particularly important. And notice the red side is identified to the red side, the yellow to the yellow, the black to the black. Okay? And I could have performed this matrix to it. So this is just sitting in the plane. I know how to multiply a picture in the plane by a matrix. Right? I just want to do that. So I'm expanding the horizontal direction by a factor of 2 and dividing the vertical direction by a factor of 2. And so I get this picture here. So this is an SL2R action. I've drawn one particular picture. There's also an R theta action. If you guys remember from Ben's talk, there's a distinguished horizontal direction. I could rotate it and get a different distinguished horizontal direction. It came from, I guess, the direction of minus theta. And also there's an action of the Horocycle 1s01, which is just acting on the picture according to that, and you shear it. People happy with this? So this is kind of key to the talk. Okay, so now rather than considering just 1s01, let's consider the entire upper triangular subgroup in SL2R. So in particular, this group is generated not just by HS, it contains HS, that's when you put a 1 here and a 1 here, and then you let this guy vary, but you can also vary over here, and we'll call that subgroup GT, and we want to think about, ergodic actions for this P. I'm about to state some great theorems of Eskin, Mirzakhani, and Mohammadi. And I should mention that these theorems also have analogs for SL2R, and they prove any SL2R, any P invariant measure is also SL2R invariant measure. And for convenience, I'll only state the P versions. But there's analogous theorems for SL2R. So Eskin and Mirzakhani have a measure classification theorem, which is that if you have a P ergodic probability measure, it's nice. Okay, so maybe I can say a little bit more about what nice means. So nice means that I look at the, so I told you about these period coordinates, which were given by the sides of these pictures. And it tells you that there's a finite number of complex linear equations in these period coordinates which cut out what your locus is. And so I think this picture is very helpful for that. And what do I have? So purple is just one side, but purple is a different side than green. And one of my equations is purple equals green. Okay? And there's another equation which is yellow equals black. And there's one last equation which is blue equals red. Okay? And so these are three equations, and this is some locus sitting in the space of translation surfaces, which is actually the support of a p ergodic probability measure, and it's cut out by these three equations. Okay. Are there any questions on this? So this is a nice object, right? It's sitting in a space with nice coordinates, and the object you're given is given by nice linear equations in this coordinate. The next thing to mention, so Ratner had an orbit classification as well, and there's also an orbit classification theorem of Eskin, Mirzakhani, and Mohammadi, where what they do is they look at the image of your point x under the p action, and then you just take the closure of this object, take the closure of this set. And what you get is also something like you could have gotten beforehand. It's something that's given in by linear equations in period coordinates. So it's just a very nice object, and so this is also such an object. So lastly, Ratner had this nice genericity theorem which paired the measure theory and the topology, which said when you wanted to know measure theoretically how a point behaved, you looked at its orbit closure, and that gave you the same answer. That told you how it measured theoretically behaved, and the same answer is true here. So they have a genericity theorem. And it says that you look at the orbit closure, and you get a nice measure like you got from the measure classification theorem on that nice orbit closure as before. And your point equidistributes according to that. So notice this is a little bit of a different average than the one I did in the case of Ratner's theorem, where it was just a horocycle average. So I take a segment of the horocycle, that's my ds coordinate, and then I also push it under the e to the t 0, 0, e to the minus t, this diagonal subgroup, and I average that whole thing. Okay? And that goes to the nice measure on the space. So every point equidistributes according to the p action, according to the measure that lives on its orbit closure. So this really nice pairing. Right? So these were amazing results that really, in my opinion, transformed the field. I think people will talk later in this conference about kind of how ideas and the proofs of this have moved on to other areas and been very profitable there. I think other people will talk in this conference about how questions that this really showed are very important. It threw into relief, like classifying what these invariant measures can be, how big they can be, things like that. But I'll just take a moment to, if you just take the theorems themselves as a black box, they're also extremely useful. So you can ask a question about a translation surface, like the picture one I have here. Imagine I just lit up a light source here. There was a point mass of light, and the light flowed out over the whole space. Will it light up all of the surface? This was answered by their results. So that's what I mean by illumination problems. It showed up a little bit in Ben's talk, but you can do the best, kind of the best counting results that hold true for every surface are either Ben's results or averaged counting results that follow from their theorem. And the reason why it's averaged is they need this extra t out here. Okay? And so you also get new types of genericity results for other subgroups of P. There's been probabilistic results, large deviation estimates have been proven using their techniques. So it's really transformed the field, from my opinion, and is a fantastic set of results. Right? So, but it leaves a natural question, which is, what about HS rather than P? Okay? So I don't want to act by the whole upper triangular subgroup. I only want to act by the 1S01. And the question is whether you still have Ratner-type theorems there. And so for the purposes of this talk, we'll restrict ourselves to the space of translation surfaces with two cone angles, each of which have angle 4 pi. Okay, so this is the name of this H11. This is a particular stratum. Every picture I've drawn so far, and I think other than the torus picture, but every other picture I've drawn has been a picture of a surface in this, and every picture I will draw for the remainder of the talk will be a surface in this space. Okay? And And so the first thing is that genericity fails. You have a residual subset of H11 where you don't have equidistribution with respect to any measure. So what you can do is you can push your point along the Horocycle flow and you average your orbit segment. And along one subsequence, it looks like it's going to one measure, as well it has to because of compactness of the weak star topology. And along another and non-divergence of Horocycle flow. And along another subsequence, it looks like it's converging to a different measure. So under Horocycle orbits don't have to equidistribute. Okay. I should also mention that this is true for a residual set. That's the sets that are big in the sense of the Baire category theorem. These are dense G delta sets. And a lot of nice sets of translation surfaces are dense G delta sets. So for example, there exists a translation surface whose horizontal flow is uniquely ergodic, and yet under the Horocycle flow, it doesn't equidistribute to any measure. Similarly, that it doesn't diverge under Teichmuller geodesic flow either in the forward or backwards directions, because these are all residual sets. So it's in some sense a big set. Okay, now what if you do equidistribute? Maybe we can understand what you belong to if you do equidistribute, but the answer is no. You could equidistribute to one of these nice measures given by Eskin, Mirzakhani, Mohammadi, in particular the picture I drew for you guys beforehand, and yet you don't belong to the topological support. So even though you start off, somehow 100% of the time you're within an epsilon neighborhood. And for the purposes of this talk, by 100% of the time, I mean, you look at the time that you're landing close, you divide by the total amount of time, and this converges to 1. It doesn't mean it's true all the time, just 100%. So this is another result. And then perhaps our most striking results are for orbit closures. And what we show is that orbit closures don't have to be nice. In fact, they can have fractional Hausdorff dimension. And perhaps even more crazy, they can live in a continuous one parameter family of properly nested orbit closures. And in the settings of homogeneous dynamics, or the theorems of Eskin, Mirzakhani, and Mohammadi, every time you're properly nested in a bigger orbit closure, you gain a dimension. You're in a finite dimensional space, so you can't even get countably many things properly nested, but here you can get uncountably many, a smooth one parameter family. Okay? So are there any questions on the statements of these theorems? So if you noticed, I started off both of the things with measure classification, because these are somehow the big, perhaps the very key results of these, and I didn't say anything against measure classification, because we have no counterexamples, but what we can say is that a key tool doesn't hold, okay? And so this is Ratner's shearing property, which I will state in an idiosyncratic way. This is worse than one would imagine stating it in homogeneous spaces, but in a way that at least I could imagine it possibly being true for the space of translation surfaces, which it's not true. But seems like it would be a reasonable thing to look at. And what is the statement in words? The statement is that if you spend 90% of your time close to another point, you have to spend very, very close to another point. You have to spend all of your time, not just 100%, but all of your time fairly close to your point. That's the idea. So
can you go back a couple of slides? So in these cases where the Hausdorff dimension is fractional, what is the associated invariant measure? Is there an invariant measure here, or is it more than one, or what is the support of the invariant measure?
Yeah, so there will be points in this orbit closure which will have that the support of their measure is in sublocus. That's a nice. So these are where are we headed? So you look at the picture I drew from you a little bit ago when I was talking about this. You look at this picture. There's ways to push yourself off of this picture so that your measure under the Horocycle flow will give full measure to the nice measure on this space. Okay. And there'll be actually a lot of stuff like this. And this could possibly be an orbit closure could live here. And a lot of these points then will live on this smaller thing. Now, there'll be other things that have other measures in this, but that's kind of the basic idea. Did that make any sense?
So the measure is smaller than the set of orbit closure.
Correct. The measure is, the support is a nice, we have examples where the support, where it's ergodic for a measure we can identify, and that ergodic measure has a nice support whose Hausdorff dimension is an integer, which is strictly smaller than the Hausdorff dimension of the orbit closure. Did that maybe answer it better? Okay, but don't worry if this doesn't make sense yet. Most of the rest of my talk is to explain what's going on with pushing out of this nice locus.
So just one more.
Yes.
Along those lines. So your very first example was you have a Horocycle orbit which is not equidistributed. It doesn't converge to any measure. But the measures that it accumulates on are all, so to speak, geometric measures?
Unclear.
Unclear.
Yeah,
Okay.
unclear. Yeah, there's a lot of stuff we don't know.
Okay, but if there were a measure classification of the most optimistic type, there would only be countably many possibilities for the limiting measure, no? If the limiting ergodic measures.
Yeah, so I guess there's uncountably many because you can push by things, but I mean, they're
I
in
see.
families. Right?
I see,
Yeah.
I see. So it could be that it's accumulating on things that are all in one push of,
I don't even want to speculate.
okay, I got it.
But thank you for the question. Okay, so right now I want to be completely upfront. We have no counterexamples for measure classification, but we do have a counterexample for a key tool, which is I imagine I have 2 points which spend 99%, let's say 90% of their time very, very close together. So delta is way, way smaller than epsilon, and that tells you that for all time they're within epsilon apart. Okay? So up to time capital T, I spend 90% close together. So then all of the time, not just 100%, I'm quite close. I'm epsilon close. Oh, yes, UT is HT. Thank you. Thank you. Yeah, sorry about that. Thank you for pointing that out. Okay? And so I'm telling you that this is false. So I want to make a statement that is correct statement. So you could find a pair of points, Q and Q prime, suggestively named, so that under the Horocycle, now the HS Horocycle, not the UT Horocycle, but under the Horocycle, they're as close as you want for 100% of the time. And yet there'll be an infinite subsequence where they move away from each other. And moreover, these subsequences will be in some compact set. So just because you spend all of your time close together doesn't mean that you belong to each other. You can really separate. And this actually sort of fits into the idea that you could be generic for something smaller than you. You could come into that smaller object, then you can move away. You started far away, why won't you ever come far away again? Okay, so are there any questions on this particular? This is probably the most technical of all of the things I stated. So any questions on this? All right. Okay, so now I need to tell you a little bit about, so now I want to spend the remainder of the talk talking a little bit about how these results are proven. And so in order to do this, in Ben's talk, translation surfaces were shown as an interesting object in their own right, and my talk began with thinking of them as a point in a space. At this point in my talk, I'm going to turn again to thinking of them as interesting objects in their own right, which have their own dynamical system on them. So they're points in a space that has an SL2R action, but they're also going to be themselves spaces where there's an R action on the translation surface, just thought of as a space in itself. Okay. And how do you get this action? You get it by lifting from the charts on R2. So we have nice charts to R2, and on R2 there's a straight line in a given direction. That makes sense in R2. And so you can lift it according to your, from your chart up onto your surface. And of course you'd worry about when you move between different charts that this gets all confused and messed up. But because your transition functions are translations, and translations preserve angles and orientation, this works out perfectly well, and you end up with a straight line flow in every direction, which just comes from lifting the same flow on R2 via your chart. Okay? And as is often the case, a picture is worth 1,000 words. So I want to draw you a little trajectory in this dotted black line. So this dotted black line, it goes up, it hits the green, so it should follow the identification. And then so it comes out on the identified part of green. Then it hits the red, so it should follow the identification in red. And yes, it does. And then it'll come back to blue and keep going. Okay? So this is the straight line flow. I'll call this the flat dynamics. Okay? And the SL2R action on the space of translation surfaces has been very profitably used to understand the flat dynamics. And I like to think of this project as a little bit of the flat dynamics giving back. we will take something that comes from the flat dynamics to show new interesting phenomenon of the, I hope interesting phenomenon, of the horocycle flow on the space of translation surfaces. Okay, so that's where we're headed. Right? Okay, so we need some context. So we need to talk a little bit about this flat dynamics. And it turns out that this straight line flow is typically uniquely ergodic. It typically equidistributes in the translation surface, and that's by results of independently of Maser and Veach. If you kind of look at the typical flow on the typical surface, and by Kirchhoff, Maser, and Smiley, if you want to fix your surface and talk about the typical flow in those. But in any case, in large generality, the flow is usually uniquely ergodic. Okay. And it's very important from our work that there's examples where the flow is minimal but not uniquely ergodic. So minimal means that every point is dense. So if you look at its orbit closure, you get the whole thing, but it doesn't equidistribute. Okay. All right, so where we're heading is we want to produce points that have weird horocycle behavior. And in order to produce these points, we're going to try and define a cousin of the horocycle flow. So we're going to take a surface, we're going to perform this cousin of the horocycle flow to this, and then we're going to perform the horocycle flow to that point. And we're going to study the dynamics of that. And in order to generalize the horocycle flow a little bit, I want to go and unpack what the horocycle flow on the space of translation surfaces is. So what I want to do is I want to kind of more pedantically describe what the horocycle image of a translation surface is, which will be another translation surface. Okay? And so if you looked at how things started, I drew you a picture of a translation surface. I drew you a picture of its chart, and it had 6 sides, 6 kind of sides that came in pairs. So 12 total sides, 6 that came in pairs. And I said you acted on this picture by SL2R, and that gave you your new translation surface. Okay? But I want to tell you side by side what you do for the particular subgroup that we care about, which is 1S01. Okay? And so what I can do is I can look at the horizontal component of this curve. I just integrate it with respect to dx. And I could integrate it with respect to dy. And I want to know how fast I shear. Well, if I'm shearing for time, I'm doing horocycle for time s, well, I take my new horizontal coordinate is going to be the old horizontal coordinate plus s times the old vertical coordinate. And the vertical coordinate stays the same. Okay? This is just how 1S01 acts on vectors. And so I've just pedantically drawn that out. Okay? Are people happy with this? Great. Okay. So it's going to be worthwhile to notice that this horocycle action plays very well with the flat dynamics in the horizontal direction. Why is this? It's because it sends horizontal directions to the horizontal directions, and it preserves length along the horizontal direction. So the horocycle flow gives you a topological conjugacy between the horizontal flows on different surfaces. Now, this is just a very special example of something much more general. If I took a translation surface and I multiplied it by a matrix in SL2R, I get a topological conjugacy between 2 different directions of flow, one on the starting one and one on the other one. Indeed, directions on one of the surfaces is sent to a direction in the other one just by how SL2R acts on the circle. But I'm lying to you. It's going to stretch things a little bit. So it's not going to be topological conjugacy with the speed 1 flow. It'll be some speed up, which is the amount you stretch those lines. And in the special case of the horizontal flow in the horocycle, you preserve the line and you don't stretch at all. So it's just a topological and measure theoretic conjugacy between these objects. Did that make sense to everybody? That's kind of an important thing in what we're doing. Now, I mentioned that you have surfaces that have more than one invariant measure. And so, you know, the Lebesgue measure sees a surface in one way, but each ergodic measure sees a surface in its own way, and each invariant measure sees a surface in its own way. Now, they're invariant measures for the horizontal flow, so they preserve flow trajectories. So horizontal distances are preserved, but in the transverse direction, there's a different distance notion. And you can draw out what your picture looks like according to this different distance. So if people are, I'm sure most people here are very familiar with transverse invariant measures, you get a transverse invariant measure associated to this different measure, and you want to measure the transverse, you want to look at what that assigns to your arc gamma instead of what dy assigns to your arc gamma. But if you're not comfortable with that, you could just look at your invariant measure, you could disintegrate it along vertical lines, and you could get a metric along vertical lines, and you could compute this here. And what we're going to do is, instead of Horocycle flowing with respect to Lebesgue measure, the obvious coordinates you see, we're going to do it with respect to a different invariant measure, an ergodic measure's coordinates. It's going to see the translation surface in its own way, and we're going to Horocycle flow according to that. Okay? And we'll call this the tremor map. Okay, so what we're doing is we're starting at the same point we wanted to start out before. So this is integrating your thing against dx, and this is integrating dy. But when I look at how it changes, I'm not doing it according to how Lebesgue measure says it ought to change. I'm doing it how a different invariant measure says it ought to change. Okay? And so this is telling you how I would change one period. And if you look at how I change all of the periods, that would spit out for you a new translation surface. Or, as you let S vary, a one-parameter family of translation surfaces. So this is the key construction for the purposes of this talk. So does anyone have any questions about this? Yes?
This is a time change of the usual Horocycle flow?
No, it's just a different thing. Okay? So in particular, what we're going to see, spoiler alert, we're going to start at our locus that I drew a picture of at the beginning, this very symmetric locus, and we're going to see that at certain special points, this is an interesting object that pushes you off this locus, right?
But it's only defined along surfaces which have more than one. I mean, it's only interesting on surfaces which have more than one invariant.
That's a great point to emphasize. So this, you could think, so there's some choice involved in this, and one of these choices is the invariant measure. And on most surfaces, on a full measure set of surfaces, this is not an interesting choice. But on some surfaces, there is an interesting choice involved. Okay? What? Are there other questions on this? Thanks for the question, by the way.
Well, it's sort of a question and comment. So the original Horocycle flow has an associated Beltrami differential for people in traditional type Miller theory, and it's dual to a quadratic differential or one form. It's like omega bar over omega. And is this the same as basically taking that and multiplying it by a suitable L infinity function that, say, is constant on the leaves of the Horocycle flow?
I don't know for sure. There's another way to think about this. So I'm sorry, I'm going to take an aside and talk to experts for a moment. I apologize for that. So there's this, so Veach gives a topological conjugacy between different between different surfaces with different invariant measures, but the same topological dynamics. He does this for ITs, but you can just look at zippered rectangles and do this. So what you can do is you can conjugate to where your ergodic measure is Lebesgue. You can do Horocycle flow there, and you can conjugate back. This is what the tremor does. Okay. Did that answer your question, maybe?
I think it says yes.
Okay. All right, are there other questions? And sorry for most people about that aside. Okay, so I want to give you a picture of a tremor, and it's the only picture I can draw, and as such, it's a stupid picture, but why not? So what's a tremor that we can do here? So if you go back to this very first picture we drew, you'll notice that these look like they're disconnected, except the blue is identified with blue and red is identified with red, okay? So the horizontal flow leaves one of these invariant, okay? And so I can do a tremor, and the tremor just says Horocycle one of these, whichever it lives. So if I look at the invariant measure that gives full weight to this, I would only Horocycle this, and I wouldn't Horocycle this at all. And so I can't draw pictures of the more interesting ones where the horizontal flow is minimal, and so you're kind of pushing everything but at different rates, but it's some kind of a measurable analog of this, okay? But unfortunately, I can't draw those pictures. So basically there'll be some F sigma set which is dense in your space, and you'll be Horocycle flowing with respect to the distance along that, at least in the case where your measure is absolutely continuous with respect to Lebesgue. Okay? And when you're singular, it's something even a little bit more mysterious, but not too bad. Okay, so I want to just take a moment as an aside that this makes sense. And what I want to justify for you right now is that the tremor map is a flow along its orbits. So I gave you a formula where when you could start at one point, you could get an R's worth of places to land along that. But I want to tell you that actually along this R, you get a flow. You don't get a flow on the whole space, as was alluded to by JF's question, but along its orbit you get a flow. And the reason why is this whole business that the Horocycle flow is a measure and topological conjugacy. So I can identify the simplex of invariant measures under the Horocycle flow with the other ones. And similarly, I can do it with the tremor, because I'm just doing basically the Horocycle flow, but I'm just changing how quickly Y is telling you to change, but still along each horizontal leaf, I'm preserving the horizontal direction, and I'm isometric along each leaf. So there's still both a measure theoretical and a topological conjugacy between these flows. Okay? And so that tells me if I tremor for time 5 and then for time 10, it's the same thing as if I tremored for time 15 to begin with. Okay? And this is actually going to be fairly useful. Okay? Yeah, so that's the moral, that it defines a flow on its orbit. Kind of a funky thing, but in any case. So the locus I'm going to talk about, as the spoilers have suggested, is this particular special one that I drew that I've shown you a couple of times before. And I want to think of this as being 2 tori glued along a slit. So if I identified blue with red over here and red with blue over here, I get 2 separate tori, but because I'm identifying them how I've done it, excuse me, I've cut open my 2 tori and I've glued them together. Okay? And this is going to be a closed SL2R invariant set. This is the support of one of these nice measures given by Eskin, Mirzakhani, and Mohammadi, or an orbit closure given by them. And it has a nice 5-dimensional measure, mu sub e, and it's the measure given on the area 1 locus by these coordinates. So let me just mention there's an obvious involution on this space, which is just slide the left over to the right and bring the right over to the left, just exchanging the 2 tori. Modding out by this gives you a nice projection onto the space of tori, SL2R mod SL2Z. Okay, so this really comes from the space of tori, and you're just doing a branched cover over 2 points of it. Okay. All right, so Katak and Stuypen and independently Veach, which was then interpreted geometrically by Macer and Smiley, showed that on this particular locus, you have some directions where the horizontal flow is minimal and not uniquely ergodic. Okay? And so the moral of this, for the purposes of our talk, is that we get interesting tremors on this space. Okay? So their tremor operation on this locus is not trivial. We can do something interesting. And what we do is actually quite interesting. I mentioned that we project down to the space of tori. So if you have a minimal flow on the place you started with, it projects down to a minimal flow on a torus. These are all uniquely ergodic. So what could be going on here is that my invariant, if I have a different invariant measure, it has to be distributed along the 2 tori differently. So recalling the picture, so it has to give more weight to one of these tori than to the others of these tori. Okay? And so the interesting tremor we get pushes us off this locus because it will horocycle flow one of the sides faster than the other. So if you remember the place where I was talking about the tremors I could draw, you just horocycled one side and you left the other side invariant, unchanged. Morally, what's happening in in this situation is your horocycle flowing faster at one side than you are with respect to another. That's a slight lie, but morally that's what's going on. Okay? And in doing this, you wreck the symmetry of the surface, so you're pushing yourself off this nice locus. And you can also think for a moment, and you can think, well, there's different ways you can kind of effectivize unique ergodicity. So you can kind of have a yardstick to measure how not uniquely ergodic something is, how different an invariant measure or an ergodic measure is from Lebesgue. And if it's quite close to Lebesgue, you're going to leave very slowly from this locus. You're going to be moving one side at speed 0.51 and the other at 0.49, for example. But then there's other pictures you can do where they're very, very close to being, where it's very different than Lebesgue, and maybe you're moving at speed 0.75 on one side and 0.25 on the other side. Okay? Did that make sense to everybody? So the speed at which you leave this locus depends on your starting point. And at plenty of points, you can't even leave it at all. Okay? Now, what I want to say, though, is things are crazy. You've got this full measure set where you have no interesting tremors, and yet tremors vary nicely. They vary semi-continuously. What do I mean by this? What I mean is if I take a limit of surfaces converging to another surface, and I take horizontal flow invariant measures on each of those surfaces, And let's assume that they have a weak star limit. The subsequents always will. That has to be a horizontal flow invariant measure on the limiting surface. So in particular, every uniquely ergodic surface, which is a full measure set, has an open neighborhood around it where all of the invariant measures of surfaces in that open neighborhood are very, very close to Lebesgue. Okay? So this is what I mean by semi-continuously. Of course, since the uniquely ergodic guys have full measure, there's no continuity because these can approximate a guy off of them and you can get something interesting. So it's only kind of some kind of semi-continuity property. Did that make sense to everybody? Okay. Okay, so what's the moral of this? And this is kind of key for our construction of the point that's generic for a measure whose support it's not in and for the failure of Ratner-type shearing. You can find an open set of full measure, an open dense set, so that when you lie in that, the tremors of any point in this open dense set move away from this E locus at speed at most epsilon. The invariant measures are all extremely close to Lebesgue on this. Okay. And now there's another key ingredient that's coming into the talk, which is that the tremor map commutes with the Horocycle flow. Okay? And this is more or less by definition. If you looked at the slide where I give you kind of the pedantic definition of the Horocycle flow and the pedantic definition of the tremor map, and then the fact that you get a topological and measure theoretic conjugacy between both the tremors and the Horocycle flow, you just notice that the numbers are the same. It's just arithmetic, like in the sense of adding the same numbers in different orders. Okay? And so this tells you that if you Horocycle flow your time one tremor, it's the same thing as time one tremoring your Horocycle flow. Okay? And this is going to be what's key for our construction because you're going to Horocycle flow and land in a set that you can understand what's happening for the tremor there. Then you're going to tremor off of that. And that's going to tell you what would have happened when you started with the tremor and flow forth. So we want to cook up a point that has a weird Horocycle orbit. So what we're going to do is we're going to take a point, we're going to tremor it. But to understand that Horocycle orbit, we're going to Horocycle our starting point and then tremor from the points along that, which we're allowed to do because they commute. And in particular, to do a particular example that's very important for our case, if I have this time one tremor of omega, it might not be in U. But imagine if omega might not be in U, but imagine that HS of omega is in U. I didn't know where omega was, but HS of omega is in U. That tells me that the time S Horocycle flow of the time one tremor of omega has to be close to the time S+1 Horocycle flow of my starting point. Right? So I've used the commutation to understand more than I would naively expect about the push of the point. Should I say those words again? Are people with me at this point? Yeah. Okay. So there's something that's mysterious. I have this cousin of the Horocycle flow that I can't even draw for you. Right? I can't draw interesting examples for you. And I want to understand its Horocycle orbits. A point I get from tremoring for time one. This is a mysterious operation, and yet I want to understand its Horocycle orbit. So instead, I want to understand the Horocycle orbit of the point I started with, and along that orbit, tremor upwards. And I'm allowed to do this because they commute. I can tremor or I can Horocycle flow in whatever order I wanted with. So I started with some kind of bad point. Maybe it wasn't in U. Maybe things were very, very singular with respect to Lebesgue there. But I know that when I Horocycle flow it, the invariant measures look quite close to Lebesgue. But that tells me that when I Horocycle flowed my tremored guy, which was pushed off of my locus, that's the same thing as Horocycle first and then tremoring, but those move very slowly away from the locus. So where we've been able to find kind of this mysterious point still had to have, at least at this one moment in time, gotten back close to where it was built from.
So maybe the steps so that HS trem1 is trem1 of HS, and then since HS is in U, trem1 is the same as H1.
Yeah.
And then H1
Or
HS
almost
are
the same.
HS, H1. Okay.
Yes, thank you for saying that. That's perfect. Yes. Okay.
One other question. So you keep saying you can't draw a picture, but I have a picture in mind. So it's right. Maybe it's wrong, but my picture is the ordinary Horocycle flow takes a rectangle and then goes turns it into a parallelogram, and that this one does the same thing except the edges are jagged now.
So you can still also draw the picture where you move the sides, each side at constant length, at kind of constant speed locally in period coordinates. Because you just, yeah, so you move to the world of different coordinates, right? So if you're fixing a point along that leaf, it's going to move differently, right? But you can still think about the side. The image of the side won't be the side of the image, but you still have the image of the, you still have an analog of that.
But won't the image of the side just be a sort of a jagged path rather than?
Yes, it will be a jagged path, but you can still just connect your two singular points and get a straight line. And you can, and those move nicely. Did that answer your question without confusing things too much?
So.
Okay. Okay. Okay, so now what's the moral of the story in this is that if under Horocycle flow you landed in omega, then when you tremored off of it, you didn't leave, you landed in U. When you tremored off of it, you didn't move very far away. So when you Horocycle flowed your tremor, you now know that you were close to where you, close to the locus you started in before you even tremored anything. And this is somehow the key thing in the talk. Right? Okay, so now we want to actually use this to get results. So I'm very fortunate that my co-authors, John Smiley and Barak Weiss, in addition to Matt Bainbridge, tell us a lot about the Horocycle flow of surfaces in this special locus. Actually, many more locuses than this behave. And what they tell us is they tell us that under the Horocycle flow, they equidistribute according to the nice measure that Eskin, Mirzakhani, and Mohammad give us on this locus. Okay? So in particular, any open set of full measure, you'll spend 100% of your time in, which remember doesn't mean all of your time, it just means 100% of your time. And so what this tells me is it tells me that my tremor under the Horocycle orbit, by the arguments we did on the previous slide, they have the Horocycle flow image of this point has to spend 100% of its time in any epsilon neighborhood of the eigenform locus. Okay. Okay. And moreover, using the fact that the guy it started from, this HS omega, I knew equidistributed according to this nice measure on this locus, I know that the tremor has to too, because they're tracking each other when HS of omega lands in U, which is 100% of the time. And the 0% of the time where you're off, that doesn't affect ergodic averages, so you're going to be generic for this measure. So I've now proven the second theorem, so I hope that I've justified for you why the second theorem I stated is true, why you can have a point outside of the topological support of a measure that's still Horocycle generic for that measure. Okay. This is the exact same mechanism that we get to negate Ratner type shearing. Okay, so what are my initial points going to be? My initial points are going to be the time 1 tremor of a point and the time 1 Horocycle of a point. Okay, and whenever the Horocycle image of Q prime lands in U, the image of these 2 points under that time of Horocycle will be very close together. Okay. So, and because you spend 100% of your time in U, you'll spend 100% of your time as close together as you want. Okay? So once again, how does this logic work? I want to know where HSQ is, so I look instead at HS of omega, and then I do time 1 tremor for that. And for most of the time, the cone of invariant measures for HS of omega are extremely close to just Lebesgue measure. Extremely close to a point. It's a line segment, but it's extremely close to a point. And so then when I do my tremor to use the commutation relation to figure out where things go, they don't go apart very far. You move roughly like time 1 of the Horocycle, so you're very close to time 1 of the Horocycle. And that's the whole idea. Okay? All right. So in the okay, so I said that there was a subsequence of times where these things are far apart, and this is due to kind of arguments that come from understanding these orbit closures in the bare category theorem, and I don't have time to go into that. But those are kind of soft methods that give you the sequence of times where things are far apart. Okay. So going back to, I think, a question, maybe the first question of this talk by Khazra, we really don't understand a lot. There's a lot we don't understand, but there's things we can understand, often by soft methods. Okay. Are there any questions? So in the last 5 minutes or so, I want to tell you a little bit, I just want to identify for you what the orbit closures are and kind of say kind of how the rest of the story goes. So what are the new orbit closures? So in this locus, I want to focus on things that are aperiodic. Not necessarily minimal, but at least aperiodic. And I want to look at the tremors I can get on those up to time t. Okay? So I want to let myself tremor for any amount of time less than or equal to t, and I want to take the topological closure of this. Okay? So there's a t here for what this particular object is in the space of translation surfaces, and they're nested inside of each other. Okay? Maybe not properly, but they are nested inside of each other. And these are going to be our orbit closures. Yeah, it's over a line segment. And really, actually, you could choose it just to be the extreme points because this S takes care of everything else. But let's ignore those issues. Okay. Now, we need to show some things. So the first thing we need to show is that it's an orbit closure. There exists some omega. It shouldn't be that shocking what it's going to be. It's going to be a time 1 tremor of something that starts in this nice locus that's good for Eskin, Mirzakhani, Mohammadi. And there's particular ones of those where the orbit closure is equal to this S of t.
Now I forgot what S of t is.
Okay, going back. Sorry, it's a little bit of a mouthful, but it's all of the time all of the time less than or equal to t tremors of things that are aperiodic for the horizontal flow. So I want to avoid cylinders and things for technical reasons. Okay. So this is so that's what that's how you get S of t. Shouldn't be all that surprising. They're also properly nested. Now, because this flow is pushing you off the eigenform locus, it shouldn't be that hard to believe that, the longer you push, the further away you get, right? That shouldn't be that hard to believe. And then it's interesting that the Hausdorff dimension of this is at least 5.5, and it's strictly less than 6. Now, let me say just a word on why you might believe this. So you can only do this interesting operation on the set of points that have more than one invariant measure. Yes?
Ranges over the reals in the
T
closure, but S there is just, well, suppose we chose, if they're different S's, right? No?
H sub S and S sub S.
S sub S and H sub S. So the first.
Oh yeah, this is a different one. Yeah. These two lines are separate. These two lines are separate. They live in different worlds.
What's really oh, there exists an omega. I see.
Yeah. Yeah, thank you for that question. But these two S's are different S's. Yeah, thanks. Okay. Okay, so now the guys where I can do interesting tremors on have proper Hausdorff codimension. Their Hausdorff dimension is smaller than the space, but it's not one smaller. So what you imagine naively is that you're putting a line segment on each of these. So really your Hausdorff dimension should be whatever the dimension of these things is. We know what it is by work of Chung, Hubert, and Macer. It's codimension 1/2. So that's a 4.5 dimensional thing. I'm adding a line segment at each of those. That's 5.5 dimensions. But really, there's some issues about how these line segments vary. So all we can do is show that it's less than 6. Okay. All right, so that's how you can get this interesting family of one-parameterly properly nested orbit closures, which all have fractional Hausdorff dimension. And maybe I'll just quickly say a word about how you could get things that don't equidistribute. So in what we were doing before, you tremored off of something, and yet you accumulated onto this locus, this smaller locus. So you started a ways off, and then you accumulated down onto it. So in doing this, you can tremor for longer and longer and get things that are going further and further out into the stratum, and yet they're always accumulating on, in terms of their measure theory, on this locus E. Okay? So you get a dense set of points. So it turns out that as you do this for time going to infinity, you actually get dense in your entire space. So there's a dense set of points that equidistribute according to a particular measure. This tells you that there's a dense G delta set that equidistributes along a subsequence, where that sequence depends on the point. This is just, continuity arguments in the Baire category theorem. Now, the Horocycle flow is ergodic for the nice 9-dimensional measure on this space. So there's also a dense set of points that equidistribute for the natural measure given by these period coordinates that I mentioned at the very beginning. So there's also a dense G delta set that equidistributes to that measure along a subsequence. And so you intersect these two, and there's a dense G delta that equidistributes according to one along a subsequence and another along a different, and so they can't equidistribute according to anything. So I'll stop there.